the usual protocol of thanking the organizers and so forth, I usually forego because it always sounds a little bit glib to my ears. But in this particular case, I am truly thankful for the organizers of this conference, and just in general for the whole community that's managed to keep going and keep doing physics and keep exciting each other, keep interacting with each other in times that are so frightening and so unpleasant that I think it's very easy to become depressed, whatever. And I am very glad, proud, and happy to be part of this community, part of this international community, which I personally find of enormous personal support. So thank you, organizers, and thank you, everybody. I'm going to begin now. What I want to talk about, now this is, I decided not to give a broad overview about complexity and black holes, but to focus on a particular problem, which has been of concern to me for some time. It's the problem of what do black holes do? How do they behave? The interior, when I speak about a black hole, I usually mean the interior of the black hole. I'll use the term that way now. I'm interested now in what black holes do, what their interior is like at exponential times. Exponential times, I mean exponential in the entropy. Very, very long times. And I think there's good reason, very good reason to believe that something different, something perhaps that you could call a breakdown of standard classical general relativity, happens inside black holes at exponential time. What is it that happens? How do we describe it? That's, I think, not known or not well known. Not known, I don't mean not well known, but I mean we don't know very well what happens. And I'd like to sort of discuss it. Now, usually when I give a talk, I'm not a very rigorous mathematician or anything, but I usually have a sense that what I'm saying is right. In this particular case, I'm kind of uncertain about much of what I'm going to say. Nevertheless, I think it's worth saying because I think it is a big and interesting, outstanding problem about the relationship between quantum mechanics and gravity. Okay, so hold on, let me just see. Yes, I do have my laser pointer. Good. Can you see my laser pointer?
Yes.
My cat loves that. We sit in front of my computer and I do that and my cat goes crazy. Okay, so here we have a Penrose diagram for a black hole, and the lower part of it here is usually called the white hole region. The upper part of it is called the black hole region. And I've foliated the diagram with a series of space-like surfaces. And those space-like surfaces are anchored at the boundary. Now, this is a two-sided black hole. It means it's described by two copies of a conformal field theory. And the region between the two horizons, the left horizon and the right horizon, you can think of as the wormhole connecting the two sides. And the wormhole has a growing volume. You can just see it from the picture. The volume of the wormhole is 0 here. It's growing, it's growing. And in fact, if you take account of what's going on in these corners here, it's growing for a very long time to enormously large. Classically, it just grows forever. On the white hole side, we have exactly the opposite. It shrinks and from a very large volume and shrinks down. And it was a puzzle that I've been confused about for many years about what the meaning of this is. Because if you stand outside and watch the black hole is completely stationary. And it's completely clear that this doesn't have to do with the growth and shrinkage of entropy during a Boltzmann fluctuation or anything like that. It doesn't have to do with entropy. It has to do with something else. I think we now large amount of evidence that that something else is some form of complexity that bounces. All right. So what do we know about these wormholes, or what do we know about these space-like surfaces? the volume of them, the spatial volume of them, grows linearly with time, and the coefficient in front of that linear growth is the area of the horizon, or approximately the area of the horizon. That's one thing we know. Another thing, at least I think that we strongly suspect, perhaps we even know, is that the complexity of a quantum state, the quantum states are the quantum states of the boundary theory, that the complexity of those states also grows linearly for some period of time, and that the coefficient in front of that growth is proportional to the entropy of the black holes times the temperature. Now, that's a guess. It's not a rigorous statement, but it seems to work very well. And so if we put these two together and use a little bit of information about the geometry, we find that the complexity is given by the volume of the wormhole divided by Newton's constant times the ADS radius. But the important thing here is that the complexity is proportional to volume. That's called complexity being proportional to the volume, CV. All right, now what do we mean by complexity? Normally, the usual way to think about complexity is how many gates or how many elementary operations does it take to produce a certain quantum state from a reference state, which is in some sense very simple. In this case here, the simple state would be the, what's going on? I lost my laser pointer. I can't get my laser pointer to laze. Okay, I'm gonna make a laser pointer. Oh, nothing will go, everything's stuck.
Oh, that's not good.
Maybe one of the options on the top, like switching.
Well, it's not urgent. I have everything written down, but I don't know what's going on here.
Can you point with your mouse, Lenny?
I don't have a mouse. I have a Apple Pencil. The Apple Pencil should be writing, but something has gone wrong. Okay, we're gonna keep going.
Let me try plugging it into the iPad for a few seconds.
Try plugging what in? Oh, the pencil?
The pencil, yeah, just to repair it.
Yeah, maybe
that helps.
Yeah, okay, let's try it. Okay. It's not registering, no. I don't think. All right, we're okay. Everything is written down. I just can't point to it, so I'll do my best. Good. All right. Now, what do we mean by complexity? Usually think of complexity as the minimal number of basic circuit elements that it takes, or basic elements of any kind that it takes to prepare a certain state. I like to think of it the other way, that it is the number of circuit elements, or how hard it is not to create the state, but to take the state and bring it back to some simple state. In other words, how complicated or how difficult it is to restore, to shrink the wormhole back to something very small. It's just that it doesn't matter which way you think about it. It's just if I was assigned a task of taking some wormhole, which was very big, and shrinking it down for some purpose to the smallest possible wormhole, the complexity would measure how hard it is to do that. Okay, now we have the complexity curve. The complexity curve is a conjectured curve. It's a conjectured curve which we certainly don't know for sure that it's exactly right, but I'll assume that it's more or less close to being right. The complexity as a function of time, well, we start, assuming that we start with the simple zero complexity state, the thermal field double state. It starts to increase, and it starts to increase linearly. That's the expectation, that it increases linearly. And I'll call that linear increase the complexity ramp. I'm using a language that was invented for different purposes by Schenker and his collaborators. I'll call it the complexity ramp, the increase of complexity that takes place. And the expectation is that it takes place for an exponential time. I'll say 2 to the number of qubits in describing the system. But the complexity cannot increase indefinitely since complexity is bounded from above, bounded at about 2 to the n. And so the complexity has to flatten out, and I'll call that the complexity plateau. That complexity plateau lasts an enormous length of time. It's a kind of equilibrium, but it's a kind of super equilibrium, way, way, way beyond thermal equilibrium. And it lasts for a very, very long time, doubly exponential in the number of qubits, e to the 2 to the n. But on that time scale, recurrences can happen, and do happen. Recurrences are more or less accidental return of the system to the original state. Of course, it's much more likely that you'll have a partial recurrence, but I'm interested now in the full recurrence. The full recurrence where you go all the ways back. And as I said, it's an incredibly rare phenomenon, but on that time scale, and it will interest me. Now, one of the reasons I'm interested in the recurrences is because it is my claim that a quantum recurrence is described exactly by the Penrose diagram that you see before you. The white hole, the black hole, that is exactly the quantum recurrence. It lasts for an amount of time, simple exponential, 2 to the n, but it takes place in a C, a long, long-term C of time, grand range of time, that these quantum recurrences happen doubly exponentially rarely. Now, what do I think? I think that it is only during these quantum recurrences that the classical description of the wormhole actually makes sense. So I would advocate the view that the full Kruskal diagram, including white hole, black hole, is really a picture of a quantum recurrence, and that the life of the black hole is mainly spent, I'm talking about an eternal black hole, not an evaporating one, an eternal black hole in anti-de Sitter space. That life is mainly spent in this complexity equilibrium, or this complexity plateau, where nothing much happens. You just sit there and rattle around a little bit with very intermittent, interesting phenomena. The interesting phenomena that can be described classically, and that is the view that I'm going to propose. So the question is now, what happens to the wormhole at the transition point between the complexity ramp and the complexity plateau? If I had my laser pointer, I would point right at that transition. But I think you can see where it is. What is it that happens there? By what is this that happens? I mean, what is it that happens from the bulk wormhole point of view? What is it that happens at exponential time? And you can think of a number, and also what is going on during this long period of equilibrium on the plateau? How do we describe it? I can think of a number of possible answers. One is the just keeps growing theory. The just keeps growing theory says nothing happens there, or not that nothing happens, it just keeps growing. The whole idea of using complexity as a marker for wormhole size just breaks down. And the wormhole doesn't care at all about complexity, it just keeps growing. I think that's wrong, but that's one possible answer. That can be called the pseudo-complexity option. Pseudo-complexity, I'm thinking about the paper of Bouland, Vazirani, and Pfefferman. They have a slightly different idea of what pseudo-complexity is, but it basically boils down to that. All right, another possibility is it stops growing, that in fact you can extend the complexity equals volume connection to exponential times. If that's true, then is this transition sudden, as I've drawn it here, or is it gradual? In either case, what is the geometry of the interior up on the complexity plateau? Is there a geometry? Or is it just such a terrible quantum mechanical mess of complexity that geometry doesn't even make sense? These are the questions which I would like to answer. I'll give you some partial answers. The partial answers are less than I would like to be able to report, but they're as much as I can do right now. Everybody still there? I see you. Scott, you're nodding. Good, okay. Okay, let's denote a state of the wormhole that has volume V. Let's just denote it by a ket vector labeled by V. Now, I want to think about the evolution of the state as V increases, as the volume increases. I want to think about it as a sequence of states in which the volume changes by an amount which is perceptible and, what shall I say, perceptible and measurable, which means that the wave function as a function of volume goes through a sequence of almost orthogonal states, or we can say orthogonal states. The time that it takes for a state to go from itself to something which is almost orthogonal, I call the Aharonov-Anandan time. That's because I learned it from Aharonov, not Dorit, but Yakir. And we can think of the evolution as a sequence of states which are classically distinguishable from each other, or at least distinguishable from each other. And in that sense, they define a clock. The volume defines a kind of clock variable, but eventually you run out of states. Why is that? Because the Hilbert space of the black hole has a finite dimensionality. The dimensionality is roughly 2 to the entropy of the black hole, 2 to the number of qubits. And eventually you run out of new orthogonal states. If the theory was integrable, you might expect that what happens is what happens to an ordinary clock, that the state is just periodic. And after you go a certain amount of time, you get to just before midnight, and just after midnight, the clock jumps back to 1 o'clock on an exponential time scale. That's what you would expect if the energy levels were exactly equally spaced. And then the system would be integrable, and that's what would happen. But that's not the way chaotic systems behave. Chaotic systems, I'll just tell you the way chaotic systems are expected to behave. They're expected to behave so that once you reach this exponential time, so that you run out of states, the new state of the system beyond that becomes a linear superposition of all the previous states. In other words, to put it another way, trying to make a wormhole longer than exponential, you get defeated, and instead you make a linear superposition of states of all of the wormhole lengths with more or less equal probability. Now, this is something that I have not seen in the literature anywheres. I learned it by doing experiments myself, but it's well known to many other people, I think, and so I'll just assume either you know it or you'll trust me that it's true. Okay, now this is supposed to represent the volume of a wormhole, and after a certain amount of time, we see that what happens is it becomes a superposition of many, many different classical states of the wormhole. Does that mean that there's a sudden, sharp breakdown of classical general relativity, that classical states don't mean anything, that there's no geometry, just a superposition of geometry? I don't think so. I think this is somewhat misleading, and I'll tell you why as we go along. But I'll come back to that later. Just keep it in mind. What I want to get to, and I think the right tool for understanding this, is complexity geometry. By complexity geometry, I mean the thing that Michael Nielsen and his collaborators invented. We'll come to what it is in a minute, and I'm not going to be very detailed about it. To be detailed about it would take a whole lecture, much more than a lecture, a whole course. So I will just be very brief about it. I'm going to use it in a way that Brown and I used it in order to discuss black holes in a paper called The Second Law of Complexity. And what I'm really going to do is use a toy model of it that's due to Brown, myself, and Ying Zhao. The toy model is useful, highly non-rigorous, but easy to understand. Okay, let's, before we talk about that, let's talk about complexity and unitary matrices. Unitary matrices have two roles. One role is that they represent unitary operators. Uij, bra vector I, ket vector I, bra vector j. U, of course, is an element of SU2 to the n, the unitary operators acting on the space of n qubits. So one thing they do is they make unitary operators. The other thing they do, the same unitary matrices, is they represent maximally entangled states. Well, I don't think I need to explain that. Uij, I, j, where I and j may be in some basis, such as what we use to sometimes call a computational basis and so forth. Everybody with me? Say yes.
Yes.
Okay, yeah, that's good enough. Just, Scott has the right idea. Just put your thumb up. Okay, so what is complexity geometry? Complexity geometry is simply a geometry on the space of unitaries, SU2 to the n. It's a geometry. Now, there's many geometries on such a space. There's a very standard one, which is the bi-invariant geometry, left and right invariant geometries. And it's not the one that represents complexity. The geometry that represents complexity is a geometry which you can start with the usual metric, the bi-invariant one, and then stretch those directions which correspond to difficult directions to move in. The difficult directions to move in are ones which are generated by Hamiltonians, which each term of which involves many, many qubits simultaneously. In other words, non-k-local Hamiltonians. You stretch the directions, make them be very costly in length for directions which you think of as hard directions and leave small with other directions. That's pretty much all I'm going to say about complexity geometry. No, I'm going to say much more about it, but that's pretty much the only definition I'm going to give you now. There's a notion of penalty factor. The penalty factor is the stretching factor where you stretch out the geometry, give it a great deal of length in the directions that you want to think of as highly complex. Okay, what do we know about such complexity geometry? And first of all, it's homogeneous. It's homogeneous, meaning the same everywhere, and it inherits that homogeneity from the group structure of SU2 to the n. It's also right invariant, as opposed to bi-invariant, and if you don't know what that means, just ignore it. It has a diameter. Diameter means the largest distance between any pair of points of order 2 to the n. Now, you might be surprised by that 2 to the n. You might be surprised that I'm not writing 4 to the n. It's not important. And if you ask me about it at the end, I'll tell you why 2 to the n instead of 4 to the n. The diameter of the geometry is 2 to the n, and that represents simply the maximal complexity, the largest distance between points, or the distance to the identity operator represents the complexity of a unitary. So it's 2 to the n. The volume of a complexity geometry is much bigger. The volume of it is e to the 2 to the n. The diameter is the logarithm of the volume. Now, this is characteristic of negatively curved spaces. Negatively curved spaces, as you move out, the volume grows exponentially with the diameter. That's what this says. Another feature of complexity geometries is that they're negatively curved, in particular the sectional curvature. The sectional curvature is the curvature of two-dimensional subspaces which are generated by pairs of, they're two-dimensional surfaces. what a section is. Negative sectional curvature. The whole geometry is pretty much negatively curved. And that means when you start out two neighboring geodesics, they deviate from each other rapidly, exponentially, and that is a sign of quantum chaos. I believe that is the central idea of what quantum chaos is, that the complexity geometry is negatively curved. And finally, the cut locus. The cut locus. This is a guess. This one in the pink box, this is a guess and it's a conjecture about what a complexity geometry should do. That the cut locus is as far away from the identity as it could possibly be, which means the diameter of the geometry. I haven't told you what cut locus is, and I'm going to tell you. For some of you who know a little bit about graph theory, you might begin to suspect that this sequence of different 5 things here is very similar to the definition of a expander graph. Diameter, volume, connection, negatively curved, and so forth. And it's a good analogy, but if you don't know what an expander graph is, I'm not going to use it, but nevertheless. Okay, what is the meaning of the cut locus? So let me tell you what a cut locus is, because I think it plays a really, really central role in this whole story. The cut locus of a point. The cut locus of a point is the collection of all cut points related to that point. So what is a cut point? Take a geodesic starting at the point P. This is the cut locus of point P, and the cut points associated with point P. Take a geodesic in the geometry, the complexity geometry, or any other geometry, and take a geodesic through it, starting at it. Let's label that geodesic A of T. A just represents a point, and and T is just a parameter along the curve. It could be time, but it could just be some parameter. Could be the length of the curve itself. Okay, you can be sure that for some, I'll call it length of time. By time, I mean T. You can expect that for some sufficiently short time, that geodesic that you've drawn, that I've drawn, is the shortest geodesic connecting P with A of T. You can always be sure that for some length of time, any given geodesic is the shortest geodesic that connects you with that point A. If I had my laser pointer, I would put it down on one of these points. But at some point, typically, that I'll label TC, C for cut, that another geodesic of equal length, let's call it gamma of TC, will emerge and it will cross A of T. That's the cut point. Now, again, I wish I had my laser pointer, but I don't. Let's look at the picture. Do you see, does everybody see the point? Can it be seen clearly? A of T of C? Yes? Can that be read? Yeah, okay, good. I was afraid it was too small. All right, imagine that there's some sort of obstruction. There's some sort, by an obstruction, it could be a topological obstruction, or it could just be a big hill in the geometry that you have to go around. There may be geodesics, in addition to the black geodesic, which goes around the hill, but typically for short times, that second geodesic that connects points P with A of T will be longer than the primary geodesic that I started with. But as you let T increase, you will come, typically you will come to a point where some other geodesic, it's called gamma of TC, will have the same length as the primary geodesic. Beyond that, gamma of T is shorter than the primary geodesic. In other words, you reach a point at which the shortest geodesic connecting P with A is a member of the family gamma of T and is not A of T itself. That point is called the cut point. And as I said, the cut locus is the collection of all cut points that you get by sending any number of all the geodesics from the point P. The cut point and the cut point represents a transition. It represents a transition in the behavior of shortest geodesics. If shortest geodesics represent complexity, the cut locus or the cut points are the points at which the character of the shortest geodesics discontinuously changes. The length of the shortest geodesic doesn't discontinuously change. It is continuous, but the first derivative of it does. And so something sharp happens to geodesics or shortest geodesics at the cut locus. Why is this interesting? Because if the length of geodesics represents complexity, and if complexity has something to do with the interior of black holes, then the cut locus is a place where sudden sharp phenomena, transitions, can potentially take place. Let's go further. I've drawn here, I don't know what to call it, a second order cut. Now, again, I had intended to use my laser pointer, which I can't. But starting at P, you go a little ways and you come to the cut locus where the red family, incidentally, notice that the shortest geodesics after the cut point are not a single geodesic anymore. They're a family of geodesics. And as you move along the black curve, the sequence of red curves are the shortest geodesic until you come to a second cut point. At some second point, the green geodesic, which goes around a different obstacle, might suddenly emerge as the shortest geodesic. And so for a typical geometry, you will find a whole sequence of cut points like this and a rather complicated answer to the question, how does the length of the shortest geodesic vary as you increase T? It doesn't even have to vary monotonically, incidentally. The shortest geodesic can get shorter for a period of time, even though the black curve is getting longer. So this sequence of cuts represents transitions in the behavior of shortest geodesics. Okay, now I want to come to the toy model for complexity geometry. I'm going to apply this idea of cut locus to a model of complexity geometry. The model is due to Brown, myself, and Ying Zhao. And it seems to do a rather good job, even though it's tremendously simplified down to 2 dimensions. It seems to do a good job of representing a lot of what you expect for complexity. Okay, so what is the model? The model is the Poincaré disk, 2-dimensional, uniformly negatively curved surface mapped onto a disk. On that disk, I also want to put an inscribed regular polygon. That's the red polygon. The sides of the polygon are geodesics, even though they don't look like it. They are geodesics of the negatively curved space. And on top of everything else, we're going to make identifications. We're going to make a Riemann surface out of it. Make identifications by identifying sides randomly. Now, you have to be a little bit careful. There is one constraint that you don't make conical singularities. It's a small constraint. You can satisfy it. Up to that constraint, you want to make random identifications. Again, no laser pointer. How many sides? Well, the number of sides is, first of all, 4 times the genus of the Riemann surface. The genus of the Riemann surface and the number of sides will also be proportional to the area of the total Riemann surface. That's, what theorem is that? The Gauss-Bonnet theorem. So number of sides, the genus, the area, and I'm going to take them, all 3 of those, to be enormously large, the exponential of 2 to the n. Now that's connected with the fact that the volume of SU2 to the n is exponentially large, and I want to represent that volume of SU2 to the n by the area of this oversimplified model. That's the model. That's the model of complexity geometry. Only other statement is that the identity operator is identified with the center of the disk. Okay, what's the diameter of this geometry? The diameter of this geometry, it's the distance from the origin or from the identity out to the polygon, and it's not hard to show you, then it's not hard to see that that's the logarithm of the area, which means 2 to the n, and that means that the largest complexity, the largest distance from the origin is 2 to the n. That's why I chose, of course, that's the reason I chose the e to the 2 to the n. Okay, now, next picture has a blue line connecting the origin or the identity going out to the boundary. It's supposed to represent a trajectory in which the complexity increases. The point A of t, that's the moving point, moves out. We can think of it as e to the minus iht. Oh, there is an important point about geodesics and e to the ihts. In general, in the geometry, e to the minus iht will generate a curve in the geometry, but not necessarily a geodesic. It's only if it is both a geodesic and a killing direction that that the geodesics will match with things generated by e to the iht, but it's an important thing to know. Okay, so we're following a particular geodesic which is generated by some Hamiltonian and just following it out on this model for the complexity geometry. We think of it as following a series of unitary operators, but of course the geometry is much too simple to really represent that. As you move outward, the complexity, meaning the distance from the origin grows linearly. It grows linearly with the parameter that we could be talking about could be the distance itself, and obviously the distance grows linearly with the distance. What is that representing? That's representing the complexity ramp, the linear growth of complexity as you move away from the reference state. So that's, first of all, and how long does it last? It lasts until you get out to the diameter of the geometry, which is of order 2 to the n. What happens next? Well, now we use the random identifications. The next picture is the random identification of a particular point at the end of the blue line with some other point or some other side of the polygon. And so the light blue line is just to guide your eye. There's no light blue line, there's just a jump. And there's no real jump either. There's no real jump in the geometry either. There's just an identification. And so let me call it a jump. You jump across to a new point where you re-enter the geometry. And since you're out at the maximum distance, all you can do is to go in a little bit. But because there are so many states, so many points out near the boundary, what tends to happen with overwhelmingly probable that you will not go very far and just return back to the polygon again. Absolutely doubly exponential probability that you won't get very far and just bounce around among the maximally complex states, if you like. All right, if I plotted the growth of complexity, or really if I plotted the growth of distance from the origin, you would see this linear growth. You would get up to the polygon, and then if you notice, you look a little closely, you'll see that the complexity, I'll call it the complexity, decreases a little bit and then increases. So I've drawn that on the figure here. Now let's keep going. Let's keep going. We go out from the origin, we swing around, we hit the polygon, we jump to some new point. What happens? We very quickly exit the geometry again, go to some new point, go in, exit the geometry a little bit, and so forth and so on, almost endlessly, because there are just so many points out near the boundary. And this just represents getting caught among the maximally complex states. There are so many of them, you just bounce around on them, among them for a very, very long period of time. But every once in a while, by sheer luck or accident, you will just happen to hit the polygon in just such a way that you wind up coming inward along a radial direction and get back to the origin, or very close to the origin. That's a quantum recurrence. It takes a doubly exponential amount of time. And so you can see that this model reproduces the complexity ramp, the complexity plateau, and the existence of very, very infrequent recurrences, quantum recurrences. It reproduces a lot of other things about complexity too, which I won't get into now, the switchback effect, but this will do for now. Okay, everybody with me? Okay, 3 cheers for the cut point, 3 cheers for the Poincare disk. Let me hear it. Are you there?
Cheers.
Yes.
Okay, good. It's in a sense of enormous comfort to hear you when I'm lecturing off into the ether, into the void. Okay, now let's try to follow the shortest geodesic. The shortest geodesic, once you get out to the, it's not a boundary. Once you get out to the polygon and make a jump, the shortest geodesic will jump. You will have hit the cut locus. You can see that from the picture. Once you re-enter the geometry, the blue geodesic becomes longer than the green geodesics, which connect the origin more directly with a moving point A of t. The shortest, in other words, simply said, the polygon is the cut locus. Once you get to the cut locus, the shortest geodesic suddenly jumps and makes a transition from blue to green. What is going on there? Well, just this picture here, which I drew earlier. In other words, the point at which the transition to the plateau happens. Let's blow it up a little bit and study it in a little more detail. In particular, let's look at the green geodesics, the ones which are more direct and shorter than the blue geodesic. Those will also be generated by a kind of Hamiltonian flow, but in general, this you'll have to take my word for. In general, they will not be Hamiltonian flows which are generated by a time-independent Hamiltonian, or any curve on this geometry can be represented as a flow or a Hamiltonian evolution with a time-dependent Hamiltonian. And so the expectation, if you know a little bit about these kind of things, is that a typical geodesic, if just drawn from the class of geodesics, will be something generated by a time-dependent Hamiltonian. In other words, a time-ordered, time-dependent Hamiltonian. When you get to the point A, that's where you just re-enter the geometry, the green curve will be generated by a Hamiltonian HA. By the time you get to the point B, another different Hamiltonian will generate, another time-dependent Hamiltonian will generate the green curve that connects you to point B. By the time you get to C, a different Hamiltonian will connect you. And finally, by the time you get to D, yet a different one. What is going on? What's going on, I would claim, is that the wormhole, or the evolution of the wormhole, how to say this, is continuously changing. It's being generated, instead of by a time-independent Hamiltonian, by a sequence of time-dependent Hamiltonians, and continuously changing between the point A and D. But then what happens when you get to the point D? When you get to the point D, you get to the boundary again and you jump to someplace else. you jump to someplace else, a discontinuous transition happens, and that discontinuous transition, the length of the geodesic doesn't change, but the whole character of it, the Hamiltonian which generates it, the whole internal structure of it will change discontinuously. These continuous and discontinuous changes and short time intervals of continuous change, they are what generate the noise on the top of the complexity curve. What does this say about the nature of wormholes? What it says about the nature of wormholes is that as you make one of these jumps, the whole internal structure of the wormhole changes. Not the length of it, but the internal structure. If you'd like to think in terms of tensor networks, the character of the tensor network jumps from one tensor network to another. And if it is true that the Hamiltonians which generate these flows are time dependent, what that will translate into is that the wormhole is not homogeneous. It is generated in a way which is dependent on where you are in the wormhole. And what it should do is to create an inhomogeneous behavior to the wormhole. Another way to say it is the wormhole is probably full of matter, and full of matter with an inhomogeneous structure to it. When you get to that point, suddenly the wormhole becomes this inhomogeneous thing, and then it shrinks a little bit and then grows back. That's this phenomena here. It shrinks a little and grows back, and then makes another jump. It makes another discontinuous jump. After it's made the next discontinuous jump, it'll evolve for a little bit continuously, and then jump again and jump again. What I'm guessing, this has to be taken as a guess now, is that the post-Exp-time, after the exponential time, the wormholes have a geometry. It is full of inhomogeneous matter. And Henry Lin likes to call it a caterpillar. Why a caterpillar? Because it's long and segmented. And I'll use, well, the word caterpillar will become a technical term in this subject. That's what I'm expecting the interior of a black hole to look like after exponential time. I think it has a geometry. I think the geometry might even be reasonably smooth, but it will be different than the kind of geometry you expect for the early times. Okay, let me now summarize some thoughts. There are three descriptions that I've given you, although you might not have realized it. There are three descriptions of what the interior of the geometry does. How are we doing for time? Michael, how am I doing for time?
You've been going for 50 minutes now.
Oh,
so, you know,
well, I feel a need to continue. Sorry.
That's okay.
Yeah, it's all right, because here's the point. All right, three descriptions we found for the wormhole. The first one was this you just keep going theory, that really wormholes really don't have to do with complexity. They just grow and grow and grow. It's the pseudo-complexity idea. And I don't think that it's wrong. I think it answers a particular question. It answers the question, how many gates did the natural evolution of the black hole use to arrive at the quantum state psi of t? How many gates did it actually use the natural evolution of the black hole? Okay, then there was number two, quantum superpositions of sub-exponential states. That was this picture where once you go beyond exponential, you run out of states. Behavior of the clock, instead of registering a coherent time, just goes into a state of superposition of all possible times. I think that's a correct description for the boundary description, in other words, for the quantum mechanical boundary description of the measurable things in the black hole. The trouble is, it doesn't really say anything about the boundary description itself. It answers the question about the boundary description. I'll come back to what it doesn't do. Finally, the minimal geodesic description, the shortest circuit, the smallest tensor network, they're all the same things. The shortest geodesic, and that gives a picture, which is, you get this caterpillar picture. But what question does it answer? It answers the question, what is the minimal number of gates needed to shrink the wormhole back to the reference state, which has essentially no distance between a very short wormhole. How do you shorten wormholes? You apply operations at the ends, and those operations simply decrease the size of the wormhole from the boundary or from the horizons inward. What is the minimum number? Not the number that the natural that if you time reverse the natural evolution, is what is the minimum number that could possibly bring you back to the simple state. These are three different questions with three different answers. The remarkable thing is that for sub-exponential times, the three different descriptions are the same. We can come back to that. But at post-exponential times, the three different descriptions are different. The just keep going theory, the quantum superposition, and the shortest geodesic. Okay, which one is right? Well, I think in some sense they're all right, but they answer different questions. But let's start with the just keep going, just keep growing, or just keep going theory. The just keep growing theory gives absurd results. In a certain sense, absurd. You can see the absurdity most clear if you go to a quantum recurrence. If you go to a quantum recurrence, the state returns to the simplest possible state, namely the thermal field double. In the thermal field double, there are measurable quantities, the correlations between fields on the left side and the right side. Those correlations are large, characteristic of a wormhole of very short size. If you jumped back by quantum recurrence to close to the thermal field double, you would say Alice-Bob experiments would succeed. What's an Alice-Bob experiment? Alice jumps into her side, Bob jumps into his side, and they meet in the middle. That wouldn't happen if the wormhole was very long. Traversable wormhole experiments can succeed. In every possible way, the state of the black hole is that of a very short wormhole. But the you just keep going theory would predict that the volume and length of the wormhole was doubly exponential. That would be the time, and so that I regard as an absurd answer. So I think the just keep going theory, or what is also the pseudo-complexity idea, does not give a reasonable description of what happens after exponential times. What about the linear superposition theory? The linear superposition theory, I think, is right, gives right answers, but it tells you almost nothing, maybe nothing, about the character of the interior. And the reason I say that is because the mapping, the dictionary between boundary and interior of the black hole is itself incredibly complex. I have in the mind now the paper of Bouland, Pfefferman, and Mazurani, who just demonstrate that the bulk properties of the interior are connected with the boundary quantum mechanics by an insanely complicated map, which is random or pseudo-random. Another fact is that the linearity of states, the linearity of superpositions of states in the boundary theory does not transform the linearity of superpositions in the bulk theory. That's the state dependence of the interior. What is RP? RP is Raju and Papadimos, do I have that right? Who pretty much first pointed out. So what I would say is, yes, the linear superposition of geometries is correct, but useless. Useless for thinking about the interior. What about the third option? The wormhole geometry is governed by the minimal circuit, minimal geodesic, minimal tensor network. That, as far as I can tell, is consistent with all measurable probes, even those designed to probe the interior, and gives rise to a picture which is geometric but unusual to the way the wormhole evolves. And I think it's the only one which gives rise to a reasonably geometric picture of the interior. Okay, I'm about finished. I just want to give an overview here. Here's the history, both of complexity and, if you believe the complexity volume connection, of the volume of a wormhole. Long, long periods of complexity equilibrium, doubly exponential, where the black hole just sits at the most complex kinds of states with a wormhole which is singly exponentially long, fluctuating, changing its character from instant to instant. But it is punctuated by Boltzmann complexity fluctuations. Boltzmann complexity fluctuations, I mean recurrences, partial recurrences and even full recurrences. They are exceedingly rare, but it is only during those complexity recurrences that classical general relativity describes the interior. Only during complete recurrences does this Penrose diagram describe what's going on. In other words, the Penrose diagram itself is a description of a recurrence. That's, yeah, I'm finished. I'm finished. That's it. Questions?
Well, thanks very much, Lenny. Maybe let's thank Lenny, and maybe we can all unmute and give him a hand.
Yeah. I will say, I am quite uncertain about all of this. It's where I was pushed by the logic of the whole idea of complexity and volume and so forth. Pushed there, I feel pushed there. I don't yet feel thoroughly comfortable with it, but I think it's an important subject because, after all, not the real black hole, the ADS black hole spends almost all of its time in this kind of complexity equilibrium, and there's only these very rare punctuated periods where ordinary general relativity describes them. So if we want to understand these black holes, I think we need to understand this. Good. I'm ready for questions. Maybe I should come back. Let's see. Since I don't seem to be able to use my pencil, of course, I could always go scroll to the right place. All right, so the question is, do I want you to see me or not? I think I don't want you to see me. Go ahead. Questions?
Yeah, so there's a question by Morris who asked, could you say again what the different colorful regions of the caterpillar represent?
Oh, they just represent matter distributions. My best guess is that the growth of the wormhole, which is really just representing the quantum circuit which produced the wormhole, if this quantum circuit is generated by a time-dependent Hamiltonian, then as the wormhole grows, there will be a time dependence of the generating Hamiltonian. If you like tensor networks, you can think about it as a growing tensor network, but the character of the network along its length will reflect the time dependence of the Hamiltonian that's generating it. And so it should lead to inhomogeneities of one kind or another. If I had to guess, I would guess those inhomogeneities, in fact, it's the only thing I can think of, those inhomogeneities would represent distributions of matter which are inhomogeneously distributed through the wormhole. The wormhole, which was created for relatively short times, the wormhole which is created by the time-independent Hamiltonian, the actual Hamiltonian system, I would expect to be homogeneous through its length. So, but as I said, I'm not entirely comfortable with this. The logic of it seems to push me there, but I think time will tell whether this picture is the right picture or not. Okay.
More questions. Maybe I'll just read them in order. So there's one by Siddharth Krishnan. You said none of this applies to evaporating black holes. Do you think any of this can be generalized to the case of evaporating black holes?
Well, I don't think so. What happens, it's not, when a black hole evaporates, it doesn't go away. It becomes the Hawking radiation. Well, why don't we follow the growth of the complexity of the Hawking radiation past, let's say, past the page time, or no, yeah, past the evaporation time. And the reason is that the Hawking radiation is free streaming. It really doesn't evolve. Its evolution is trivial. It's just static. It stops evolving. So I can't see any way in which this can apply to the free streaming Hawking radiation. Now, if you manage to bottle up the Hawking radiation and collect it and bottle it up and put it in a sealed container, maybe even make a black hole out of it, of course, it would then continue to evolve, and it would be just this picture. So, but no, I don't see any direct way that it would apply to evaporation.
Thanks. Let's see. Yes, I'll read one more. Maybe people can also unmute and ask themselves. So there's a question by Jan who asks: is there a field theory computation, for example, a very late time two-point function with operators on each side that can test the caterpillar idea?
Ordinary, you might just calculate left-right correlations and try to ask whether the left-right correlations might see this junk in there. Problem is that by exponential times, the left-right correlation, I was about to say that the left-right correlation is so small that you can't see it, but that's not exactly right. Something happened. I see my own name, but I don't, am I still functioning? Everything functioning?
I think we don't see the screen anymore,
No,
but we also don't see your picture.
Okay, let me see if I can get the picture back up. What do you see now?
I see maybe your ceiling and
yeah.
your hand. Yep.
Hold on, let me.
Yeah, there we go. So now we see you.
Yeah, okay, good. All right. It would be nice if I could see you guys too. I'm not sure. I don't remember how to get this on gallery.
Let's see. Is it like a small button on the top left?
Okay, I see Ying. I see Jan. I see Scott. Good. Okay, so hi, Scott. Good. So there was a question. I can't remember what it was.
There was a question of how to test by some field theory computation the caterpillar idea. Yeah.
All right. So if you look at just left-right correlators or ordinary kind of correlators, what happens is they just tend to fall until about what I would call a page time, which means a time of order, whatever the page time is. And then they just get noisy. They get very noisy, and it's hard to see anything through them. The thing is, in order to see structure in the interior of a very, very long wormhole, you have to do correlations of operators which themselves are very complex. This is something I've been thinking about. If you were allowed to think about operators which themselves grew in complexity, got very complex, the operators that could be accessed from the outside, but which are themselves extremely complex, could you measure what's going on inside the black hole? And I don't have a clear answer right now. I would hope the answer is yes. But the question is, would those be feasible experiments given how complex the operators are? So I would say, here's what I would say. Exponentials are very, very big, except when they're not. When they're not is when they're exponentials of not such big numbers. If we had a quantum computer of 10 qubits, 2 to the 10 is only 1,000. can this kind of reasoning teach us anything about the behavior of correlations at exponential times for systems which are small enough that exponential times are still within feasible range of experiments? This, I think, is a very, very interesting question, whether Exp-times can be explored for computers which are big enough that you're sort of in the range of where you want to be, but small enough that e to the n is still within the range of measurability. So I don't know the answer, but I think it's worth thinking about. Anyway, Jan, I went off on a tangent, but that was my best attempt to answer your question. This whole business, I think, well, go ahead. Yeah, okay. Next question.
Yeah, so next question is by Isaac. Isaac asked, can you explain why you expect the decrease of complexity to be monotonic in the recurrence regime instead of just fluctuating wildly?
Well, say it again.
Can you explain why the...
Good. I didn't say what I should have said. You're asking now about the quantum recurrence?
I think so, yes, but
yes,
maybe
okay.
Isaac can clarify.
Yeah. No, the quantum recurrence is an incredibly unlikely event. But if you ask the question, conditioned on the assumption that you do get back a minimal complexity, conditioned, you just you just look for the fluctuation which does bring you back to minimal complexity. So conditioned on that, what is the most likely way that you can go from the states of very high complexity back to very small complexity and then up again? Conditioned on that assumption, or is conditioned on the question, conditioned on the condition that you achieve minimal complexity, what is the route by which it goes? And the answer is it goes by the route of the V-shaped region of the curve that I drew, which means the Penrose diagram. This has an analog for ordinary thermal physics. We're talking about complexity, which is a thermal physics on a super grand scale, but ordinary thermal physics, this kind of bounce phenomena could just be, you have a room full of gas in equilibrium, and the fluctuation is just a fluctuation in which all molecules assemble at the center of the room and then go back out. There's a particular trajectory for that, which is the most likely trajectory for it to happen, conditioned on the assumption that the molecules do find themselves at the center of the room. What is the most likely way for them to get there? And the answer is a particular trajectory. And what does it look like? It looks like the molecules all swoop into the center, swoop back out. So that's the analog here. But on this grand time scale of double exponential, which is associated with complexity rather than entropy. I don't know if I answered the question or not, but I answered some question.
Isaac says he's satisfied. His internet connection is not good enough to check with high quality. Yeah.
He's probably saying, I don't want it to go on anymore. I'll say I'm satisfied.
I'm sure that's not the case.
Okay.
Next goes Juan, I think. So he asks, Juan Malacena, he asks, what is the character of the matter distribution? Is it one particle per Schwarzschild time, or does it distort the geometry completely?
I think so. Henry and I and Wilson and Douglas have been talking about this a lot. And yes, I think it's one per roughly thermal time for the black hole. But again, I'm out of my depth. To a large extent, I'm out of my depth on this. And I don't think complexity theory, as we now know it, is going to answer these questions. So one is asking how rapidly do these how rapidly do these transitions take place? It looks to me like they happen roughly once every thermal time of the black hole, I think. And
I think
this toy model can answer it. Ying, do you remember what the time is for each one of these little jumps?
I don't remember it. We looked at it before, but I don't
Well,
remember.
but I think it's a small time. Not long.
Yeah,
But I
it's
don't
a
think it's
small time. I remember we compare our answer with the sum of Steve's calculation, and there is big time. For us, it's small time.
Yeah, but it's not super microscopic. It's not Planck time or anything like that. No, I think probably thermal time. No, it's probably transit time across the black hole for a Schwarzschild black hole.
If I could just make a small comment, I would say that you need a lot of matter also to make the wormhole very long. So.
Oh, that's Henry. I hear Henry's voice.
Hi.
Yes. You need a lot of matter to make wormholes long.
Sorry, to make them long and stationary, you need a lot of matter.
You're talking about the Euclidean, the Euclidean worm.
Right.
Yeah, I know what you're talking about. Yes, that's right. You need a caterpillar. So we now have wormholes, octopuses, pythons' lunches, and butterflies. But now we now have caterpillars. The question is, what subject are we doing? Is this physics? Is it zoology? Okay, just a random comment.
So I would
Any
suggest
other
that maybe,
questions?
yeah, maybe people can speak up themselves unless they have technical problems, and in which case I'm happy to continue reading. But maybe it's more fun for Lenny if he hears other voices as well.
Yeah, that's okay.
Let's see.
And we have necromancers.
So Sipa, do you want to ask a question still? If you're around. Okay, so maybe I'll just read one more.
Okay, go ahead.
So this is so Sipa asks, how does the story modify in cases that the gravity is dual to an ensemble average, like the SYK model?
Oh, yeah. Well, obviously, I think all of this fluctuations will get washed out. Why? Because for each member of the ensemble, they're likely to occur at a different place. And certainly, quantum recurrences will get washed out. So, but that I don't think that necessarily means you can't recover them from doing the right statistics on the ensemble. Henry has been thinking about this a lot, and he just sent me some message this morning about something I'm supposed to study in order to. I don't think it means that you cannot see it in the ensemble average, but you don't see it in an obvious way. If you ensemble average, you'll simply wash these things out. On the other hand, if you ensemble average some high moment or something of some probability distribution, you might detect that these fluctuations are there and so forth. Henry, you have anything to say about that?
Yeah, not really. I guess I would say that, well, the idea would be that instead of averaging with respect to time, you would average with respect to the couplings. And,
well, we're talking about averaging with respect to the couplings, yeah, or time, but I think you would expect that if you averaged a high enough moment of something, you could recover the fact that fluctuations were there, even though you wouldn't see the individual fluctuations.
Yeah, I agree with that.
Yeah, so which might bring wormhole, not the other kind of wormholes into it, the Euclidean wormholes and what Marov calls instantonic wormholes. But that's for the future.
All right. Next up is Andrea Russo.
Hi. Yeah.
Andrea.
Okay. I just wanted to ask if when the wormhole is at maximum complexity, if we lose any kind of classical description of it, if it is
any
like,
kind of classical.
Yeah.
Well, here's what I would say. Yeah. What I'm saying is, okay, there were these geodesics, the green geodesics, the shorter ones, those were generated by time-dependent Hamiltonians. At any given instant, the wormhole should look as if it were a wormhole that was generated by a time-dependent, but perhaps a smoothly time-dependent Hamiltonian. It's not the real Hamiltonian of the system. It's the green geodesic instead of the blue geodesic. And at any given instant, the wormhole should look like a wormhole that was generated by this time-dependent Hamiltonian. Now, if this time-dependent Hamiltonian is itself more or less a normal type of Hamiltonian that you would expect describing a black hole, except that it's now time-dependent, you might think of it as just the evolution of a wormhole in a time-dependent background of the black hole. Somebody is varying some condition in which the black hole is present, varying it with time, but the black hole is otherwise evolving perhaps in a more or less normal way. And so there might be a classical description of the wormhole. The classical description of the wormhole would evolve in a kind of funny way where we jump around in this way, but at any given instant, I think it might well be pretty classical, might well have a geometry. So not as bad as it could be. I don't think it's necessarily a total mess, but the equations governing how it evolves and so forth have yet to be given.
Okay, thank you.
Sorry, I have a quick question. You just used the language, the black hole might have a geometry. What does that mean? Like, what is the example of it not having a geometry?
Yeah, good question. What does it mean not to have a geometry? I don't know. Somehow that some idea that states can be so bad. I don't know what can be worse than a maximally complex state, but that states can be so bad that they really just don't have a classical geometry altogether. I'm sort of skeptical that any such thing exists, but you know, a lot of people have thought about that and said, could it be that states of yeah, no, I think that's all I'm going to say. That's all I'm going to say. I don't know what it means to say that it doesn't have a geometry, other than to say that nobody can find a way to describe it geometrically. You know, this all has a way of, if I were thinking about tensor network descriptions of the interior of the black hole, you can imagine as time goes on, the tensor network gets longer and longer and longer. At some point, the same phenomena of superpositions happens. When the tensor network gets too long, there just aren't new linearly independent states. And so the tensor network becomes, or the state produced by the tensor network becomes a linear superposition of shorter tensor networks. Okay, that's one description. But another description by a counting argument is that you can always find a single tensor network that produces the same state. Typically, that single tensor network will be exponentially long, but there will be a single tensor network. So one of the things that's going on here is that there seems to be an equivalence between superpositions of, let's say, tensor networks, many different ones, and single tensor networks, except that those single tensor networks tend to be not longer than exponential, but exponential length. So that is a model, in a sense. The tensor network model gives you a kind of argument for the existence of a geometry, a single geometry, even though you're in this domain where you might have thought that it's a linear superposition of many geometries. There always will be a tensor network which will produce that same state. I find that an interesting thought, that superpositions of geometries may themselves be geometries.
Why is that minimal tensor network unique?
Because it's minimal. No, it's not always unique. At a cut point, when it's not unique, you're exactly at a cut point. where there may be two of the same length.
If it's often not unique, then what does it imply about the geometry, dual
I
geometry?
mean, if it's often not unique, well, I think what it means often means every thermal time or something like that.
For example,
I
I
think
think you want
I
to
think it
assign
means-
a caterpillar according to the tensor network, but what
Yeah,
if
okay.
there's not unique?
If it's not unique, I say it is unique, except at the cut points. The cut points are places where things jump. So here's the picture. The caterpillar wiggles a little bit continuously and then jumps to a new caterpillar, which wiggles a little bit continuously and then jumps again. And every time you hit a point where it's not unique, that's a point where the jump can take place.
You want to say that after the jump, it's unique.
Yeah, between jumps.
The jump is when like you cut up the caterpillar into many pieces and reassemble it.
Right.
Is Scott still here? I remember years
Speaking
ago.
of necromancy, caterpillar necromancy.
Hi, Scott. I remember years ago I once asked you about the uniqueness of a tensor network. Does it exist, the unique state preparing the state? I remember the answer is basically
No.
negative.
Oh, no. The tensor network that prepares a state is certainly not unique. The question is
No,
what
I mean
destroys it.
the minimal tensor network. Oh,
Somebody shut him off and start him over again.
Scott, you went again to this kind of wiggly talk thing. Like if you can maybe mute and unmute, that might help.
I can also, oh yeah, Scott writes, certainly minimal circuits don't need to be unique.
No, they don't need to be unique. And when you hit a point where they're
More will
not
be
unique,
coming.
yeah. But I think I would guess that that generically they are unique. Minimal is minimal. It would require some very special symmetry or something to have them. They're not minimal at the cut points. In a sense, that's what a cut point is. Oh, also at a conjugate point. In geometry, there are conjugate points where there are many equivalent length.
It sounds like this really high requirement that the bulk geometry needs to be really smart. There needs to be the unique minimal tensor network, and somehow gravity figure it out instantly and change this entire wormhole according to that.
I don't think.
So yeah, maybe I can just add what Scott wrote in chat. So he mentioned, well, minimal circuits don't need to be unique, and he doesn't see why minimal tensor networks need to be unique either. And he made the point that there's lots of like small changes you could make in any case, right? Like little circuit identities, I guess, that you could use to. So somehow, I guess you want to quotient out those in some way.
Well, if there are lots of them, then yes, then we have to worry about them. Then there may well be an ambiguity. My assumption was that generically they're unique, and that at special points they can be non-unique. An example in terms of geodesics, are minimal geodesics unique? No, not necessarily. At cut points, they're not unique. But another case where they're very non-unique is at a conjugate point. A conjugate point is like the north and south pole of a sphere. There are many geodesics of equal length connecting the north and south pole of the sphere. Okay, that's called conjugate points. It requires a special symmetry. The conjugate points are not generic. Cut points are generic. Conjugate points are features of rather special situations.
Conjugate points really require positive curvature, whereas you've got negative curvature.
Yes, that's also true.
Negative curvature will keep you from having conjugate points.
Yeah. Is that Edward?
Yes, it was. Yes.
Oh, hi, Edward. Yes, that's exactly right. So I don't know any good reason for thinking that there's a large multitude of degenerate circuits. But if it's true, then everything I said has to be rethought.